Question 4 gets you to think in a bit more detail about what happens with a diffraction grating. So here's your setup as they've drawn it there. So you've got a series of these in effect parallel slits very closely spaced on the diffraction grating with the spacing D. And the idea is that because of diffraction, as it goes through the small slit, the light can get bent through various angles. So suppose we have a ray coming out here so that this angle is theta, and we've got the corresponding rays there which are all meant to be parallel, so I haven't drawn that very well, but get the idea. Now the thing is, let's think about first of all the first order diffraction, so the first order lines on the thing, and then we'll get on to the question which asks about the second order one in a minute. So what you have to imagine is that far away over there is a screen, and these rays are going to converge at a single point on that screen. So they're drawn as parallel lines, but really they're not quite parallel because they're just very, very slowly converging. But the screen is so far away that on this scale they behave as parallel lines, because we need to have that sort of assumption in order for this analysis to make sense. Okay, but that's the bit you've got to get your head around, that these are actually converging at a single point. Now, what we need is for the path length travelled by this one to differ from the path length travelled by that one by a whole number of wavelengths in order to get constructive interference when they arrive at that point. Okay, so because all these rays are converging at the same point over here, the difference in path length between each ray and the next one is just this distance here. So that's the difference in path length between this ray, and that is the difference in path length between this ray and this one. Okay, so what we know is that in order to get constructive interference, in other words, in order that when they meet at the same point and you get superposition, that you get a big amplitude, a high intensity, that this path length difference needs to equate to a whole number of wavelengths, because they've got to be in phase when they meet. So that needs to be different by one wavelength there, two wavelengths there for the first order lines. Now for the second order lines, they're going to result from diffraction through a bigger angle, so we're going to get lines like this. Okay, and the idea now then is that, again, when we draw that line up there, this distance is now going to be 2 wavelengths, and this distance is going to be 4 wavelengths. Okay, so that's the difference, that for the first order lines the path length difference is 1 wavelength between adjacent slits and 2 wavelengths there, but for the second order one it's 2 wavelengths there and 4 wavelengths there. Okay, so in the question it's asking about the second order image, so it's these purple rays that we're talking about, and so that distance is 2 lambda, that distance is 4 lambda, and the point is that that's necessary in order that at this point and at this point the waves are exactly in phase, so this one and this one and this one, because if they're in phase here then they'll still be in phase when they've all arrived at the distant point that they're converging on. Okay, so in answer to the question, therefore, what's the phase difference between the waves at A and D. So this is A and this is D. And the answer is the phase difference is 0, because they must be exactly in phase in order to get a bright image. If they weren't in phase, then you would get destructive interference and you wouldn't get the bright image. So the phase difference is 0 between A and D. Between waves at A and D. And then it wants to know what's the path length between C and E. So this is E, and as we've said, sorry, not this, but this, get the right place in a minute. This is E, right here, and we've said that is 4 lambda because we're looking at the second order image. So we've got a difference of 2 lambda between adjacent lines, then 4 lambda between lines, the next but one lines, like that. So 4 lambda is the answer to that question. So in part 3, we've got to demonstrate that this is true using that construction, which is the same as the one on the page there. So we can begin by realizing that it's got to be based on this triangle here, right, because we know that distance because it's 2D, and we know this distance CE because we've just worked out that's 4 lambda, so we know the distances in this triangle. So we've just got to work out what's going on with the angles in this triangle, but hopefully you can see fairly confidently that if this is theta, this is 90 minus theta, okay, because that's a right angle there, and if this is 90 and this is 90 minus theta, then in order for the angles to add up to 180 altogether, that angle CAE is equal to theta. So that's the first thing that we need, that the angle CAE is equal to theta. So that being the case, we can then say that this distance CE, so distance CE is, just through normal trigonometry, is distance BC, AC times sine theta. Okay, so that's just normal use of a sine function. But of course distance AC, you can see, is equal to 2D. Okay, so distance CE is equal to 2D times sine theta. Now distance CE, we've worked out, must be 4 lambda in order to get constructive interference. Okay, and that was in the previous part, so we know that CE, distance CE is 4 lambda. So putting those together, we get that 4 lambda is equal to 2D sine theta, and then dividing by 2, we just therefore get that 2 lambda is equal to D sine theta, which is what we set out to prove. So part B is getting you to think about the idea that as you get higher order diffraction, the value of theta increases. So in other words, the first order lines theta will be here, and then second order, and then third order, and so on. And it's saying, well, how far can you go? And of course the maximum angle of diffraction is 90 degrees, because you can't bend it, more than that. It would be bending back the other way, then you wouldn't be able to detect it. So that's the starting point, that the maximum value of theta is 90 degrees. And of course the sine of 90 degrees is equal to 1. So we've got the relationship that n lambda equals d sine theta, and so if theta is 90 degrees, which is the maximum value, we get n lambda is equal to d times 1. In other words, n lambda is equal to d. So we can therefore deduce that the maximum value of n would be d over lambda. So then we just have to put the numbers in to figure out what that is. So d is the distance between the slits, and it tells us that we have 4.5 times 10 to the 5 lines per meter. So that means that d is 1 over 4.5 times 10 to the 5, because it's the distance between the lines rather than the number of lines per meter, which is 2.222 times 10 to the minus 6. So that's the separation of the lines on the diffraction grating. So that's 2.222 times 10 to the minus 6 divided by the wavelength, and it tells us in the question that the wavelength we're interested in is 486 nanometers. So that's 486 times 10 to the minus 9 meters, and if you work that out, that comes to 4.57. Obviously though, we know that n has to be a whole number, because otherwise you don't get constructive interference. So n must be an integer, which means that the maximum value of n you could actually get would be 4. And that's the answer. Okay, question 5, part A again. We have diffraction grating question, so we know that the key relationship is going to be n lambda is equal to d sine theta. And our job this time is to find out what d is, because d is the spacing of the lines on the grating, and therefore 1 over d is the number of lines per meter, which is what we're supposed to be finding out, in effect. So let's therefore rearrange this expression first of all to find out d. So we get n lambda divided by sine theta is equal to d. So then we can put these numbers in here. N, well, it tells us that we're talking about the first order maximum. So n is 1. So it's 1 times lambda. It tells us is 7.00 times 10 to the minus 7 meters. So 7.00 times 10 to the minus 7 meters, divided by sine theta, and it tells us that theta for the first order maximum is 75 degrees, so it's the sine of 75 degrees on the bottom line. And if we work that out, that comes to 7.247 times 10 to the minus 7, and that will be meters, because d is the distance between the lines. So that means 1 over d is 1 over 7.247 times 10 to the minus 7, which is 1.380 times 10 to the 6 lines per meter. But you've got to be careful here, because it wanted to know the lines per millimeter. So obviously a millimeter is only 1/1000th of a meter, so there'll only be 1/1000th as many lines. So that's equivalent to 1.380 times 10 to the 6 over 1000. which is 1.380 times 10 to the 3 lines per millimetre. So in part B this time it wants us to find an angle, so again we've got to rearrange this time to get sine theta. So n lambda over d is equal to sine theta, and then again we just put the numbers in. So it wants the first order maximum, so n is 1 times lambda, this time it's 4.5 times 10 to the minus 7 meters. Sorry, 10 to the minus 7 meters. And d is the spacing between the gratings, sorry, the spacing between the lines on the grating, which we worked out was 7.247 times 10 to the minus 7 meters. That was from part A. Okay, so that's from part A that we get that number. And so, sorry, 7.24 times 10 to the minus 7. So we just crunch those numbers, and that comes to 0.6215. Okay, so that's sine theta, and so theta is the inverse sine of 0.6215, which is 38.4 degrees. Okay, so a lot of this diffraction grating stuff just comes down to rearranging that expression and putting the numbers in, but being careful with the powers of 10 and stuff. So for part C, again, we've got to find an angle, so again we rearrange to get sine theta is equal to n lambda over d, and plug the numbers in. So it's n, because it's considering all possible orders of diffraction now, so n can be any whole number. Lambda is 7.5 times 10 to the minus 7 meters. Divided by d, which again is 7.24 times 10 to the minus 7 meters, the same as it was in the previous question, which is 1.04 n. So if n is 0, then of course sine theta is 0, which means that the central maximum will be observed, as always. But if n is 1, then sine theta is equal to 1.04, which is impossible, as sine theta must be in the range 0 to 1, and n equals 2, etc., then sine theta is always going to be greater than 1, so also impossible. So what that means is that only the central maximum, in other words the one where the angle doesn't change, just carries on along the normal, only the central maximum is observed.